Okay. So, hi. Yeah, this is a joint work with my colleagues Theodor and Laura from Bjørner and Nikolaj from Microsoft Research. So, to make it very short, we are all, I guess, good sleeping. So, let's make a compact summary, and it is just we have a new string solver. Amazing, right? So for those of you, I mean, it is a bit unusual for Theodor, I guess, to talk about strings. So I'll make a brief recap. Yes, well, what are string equations, and in particular, what is Nielsen transformation? You might not know it, and I definitely did not mess up TABLEAUX with Kate or something like that. No, there will be something like TABLEAUX, I promise, and it's called the Nielsen transformation, which is the basis for the string solving. I will explain to you later. And I'm always super excited about talking about the stuff I'm doing. And there's a lot we did for the string solver. However, unfortunately, I'm limited to 25 minutes. So therefore, I will not talk about the last few points here. But I promise the 2 points I will discuss, the ground power introduction and the generalized Parikh image, are also pretty good. So I think it should be fine. But yeah, first, as promised, what are string equations? And it's pretty simple. I mean, I have a definition both for mathematicians and for computer scientists. So I hope you will find something that suits you. Well, for mathematicians, it's pretty easy. We have word equations, existentially quantified word equations over free monoid, and we want to have a solution for that word equation. Yes, well, for computer scientists, it's even easier and very hand-wavy as usual. Well, we want to find values for an equation that contains string variables, and a string is just what we expected of a string to be. It's just a sequence of characters. And that's actually also what's written here. For a string term, it's just a finite concatenation of string variables that just represent strings, or a sequence of characters, a finite sequence of characters. And we have the empty strings, the neutral element for the algebra people here. So therefore epsilon, or for the Java people. And string equation reasoning is just important for a lot of verification topics, like, for example, is there a potential way to bypass some security mechanism by injecting something in your cookies or something? All right. Yeah, people have examples. So here we have one. Yeah, let's take this string equation here. Unfortunately, the pointer doesn't work. Yeah, this one here, the AX y. For the Java people here, well, it's this equation. And we're asking the question, what is x, what is z, what is y, so that this evaluates the field. Simple as that. Here is a solution for it. I don't think it's the only one, but it will be one. So in this case, we just say x is a, y is a, and z is the empty string. Well, plug it in. Oh my God, amazing. It is actually true. Okay. So just to finish some definitions, I think it's pretty straightforward. The string term is just a sequence of totals. I'm lazy, so therefore I will mostly abbreviate them here by U, V, and W. And a string token is either a string variable or a character. And a character, you can just imagine as if it would be an ASCII character. They are all distinct. A is not equal to B, but obviously. And we have an interpretation, respectively, and substitution that just maps string variables to some string term. The string term in method can again contain variables, but it should be kind of acyclic, otherwise it should be strange, right? And then we have string tokens, and we extended it also by something like a power token, and it just means we repeat a certain string term given number of times. So here it says just we have the string term u, but the pointer doesn't work. Okay. With this u, and we repeat it n times, and n is just a natural number, which can be symbolic in turn, as we will see, which is the interesting part. All right, so about word equations, also a brief recap. Well, it was first shown in 1977 that the extensional equation of fragment is actually decided. Pretty cool, because people didn't believe in it before. So they were thinking, probably it's undecidable. No, my find short a ridiculously high and expensive computational approach to actually solve this. And even more, Arthur Desmond later proposed, and I think it was 2012, it's actually in p-space by using the so-called recompression algorithm, which is great. It is kind of efficient, but unfortunately, it destroys a lot of internal information about the string, which is why usual SMT solvers, so solvers that are used to reason in the combination of theories, use incomplete approaches. Like, for example, they reduce the string equation to a set of automaton theories, so regular expression theories, or they unwind, they encode into SAT. I mean, there are different approaches. But most of them just rely on something that's called instant transformation. And this is the amazing point where the tableau comes into play. Yay. Because instant transformation can be represented as a tool. And in particular, my calculus here is strongly based on the instant transformation extent. Okay, so far so good. These are string equations, and now let's quickly also talk about the instant transformation. And it's very easy. So the high-level idea of instant transformation is just you look at the very first token of a string equation. So let's assume you have the first token U, T on the left-hand side and S on the right-hand side. These are just tokens, some string variable or a character, and then preceded by some U or S, U or V on the right-hand side. And the only thing we have to do is to line this T and this S. We don't care about anything else right now. And we do so by just splitting. Is T a prefix of S or vice versa? That's the only thing we do, and then we prune the input prefix. Amazing. Let's say we make progress. We don't. Let's wait for now. And we do so until we reach the trivial equality if the empty string is the empty string. Well, cool. And whenever we encounter conflict, then it's just back. So to give us an example here, let's consider again our previous equation here. We just compare this A, which is the constant character here on the left-hand side, with the Y, with the variable Y on the right. We just care about these two tokens. We just check whether A is the prefix of Y or Y is the prefix of A. That's all. And we usually represent it by an unsigned tableau calculus, depending on how you would like to look at this structure for that. Here are the rules, or here are some of the rules. Assuming you have the one that begins with a true character and the other one as well, and they are different, well, then we have a conflict, we backtrack. Same if we say the right-hand side and the left-hand side is empty, there is nothing, but the other side wants to start with the character. All of it. If we have a common prefix, well, we just stop it. And in case one side is just the empty string and the other one starts with the variable, we just apply where this variable is the empty string. Okay, so good, so far so good, but now there are more tricky rules. For example, if the one side starts with a constant, but the other side is a variable. Now we have to do a split. This is painful because now this grows exponentially. Either the variable itself is the empty string, or this variable starts with A and proceeds by a prefix, which is just a fresh variable. So let's say X prime. Similarly, if you have on the left-hand side a variable, on the right-hand side a variable, we have to split either they are equal, one is a prefix of the other, or the other is a prefix of the other. Just shown here, the red cases will be the really problematic ones, and we will see later why. For now, just keep in mind, the red ones, not bad. Just to show an example, I will not go through it in detail, but assume we have our equation here as before. We start here, and we just apply the rule, either y epsilon, because here the y and the comparative against the A, or the y substitution. And we do so, for example, here we get a conflict, but here we can go on, until we eventually hit here a wonderful case of epsilon is epsilon, showing, yes, there is indeed a model, and we, in fact, we can construct it from this. So I should now say, amazing, great, we solved it. There is nothing interesting to say about it, but unfortunately, I still have 50 minutes to go, and the page count is also not yet where it should be. It's not because I'm in the appendix. I will show you there are a lot of problems, but at least there's one good thing. Instant transformation is sound, and it's at least silly complete. So that means if there is a model, we will actually find it. However, it's not terminating. So therefore, we extended the news rules by a couple of rules that make it terminating more often, but I promise we will not terminate on all instances, unfortunately. Okay, just motivating it pretty shortly. Let's take another equation, a bit more problematic one. This one here. Well, we can either split, well, yeah, X would be empty. Yes, okay, conflict immediately. Or X starts with an A. Okay, well, we could go on and on and on. And I tell you, I can do this as long as I want. I can always find a new equation that looks different, but always if you split on the epsilon case, it results in a conflict. Okay, so I tell you, Nielsen on its own would just that. There's nothing we can do. So we just add a new rule. And in particular, we will use this one, which was first. We just abbreviate this infinite chain we saw before, this one here, by, well, we repeat A a couple of times. Let's say n times. And we just make the symbolic here and say, well, X is an n times repetition of A. We plug it in, so cancel out the prefix, and we get a conflict. Left-hand side starts with an A, right-hand side starts with a C. Great, it's a compact representation, but very compact and short tableau. So to make it a bit more formal, I introduce here the ground power introduction. And the idea is just using these powers in a more systematic way. So power is just a repetition. So for example, this term here, which even contains nested powers, just represents this string. And the ground power introduction is a very simple rule. Actually, it's not simple because this here is the version for only one string equation. There's a more complicated one that puts multiple equations into relation with each other. But for now, to fix it, let's consider only this one. If we have on the right-hand side starting with an X, and on the left-hand side we have a prefix W, and then it proceeds with an X, and this W is variable free, then it follows always that X, if there is a solution, then X has to be of the form of n times repeating this prefix, repeating this W, and then followed by potentially some prefix of the W. Okay, well, yeah, there are some open questions. For example, what is n and what is W prime? Well, easy solution for n will we just keep symbolic. There is an n. So let's make it an SMT solver's integers product. Then make it an SMT solver's integer reasonless problem. So that's easy. And as we also assume that W is variable free, which is a restriction we can partially stop actually, but for now it is variable free, then the potential set of prefixes for W is finite. We can just brute force it. We just can list all potential ways of finding the prefix for W, even if W itself contains a power. Okay, so we have some examples. Considering this example, this equation here. Well, there are two cases. Either X is a repetition of ABs, well, we can plug it in, get a concept. Well, we can also try X is AB to the power of n, and then preceded by a single A. Well, we can try that, and again, yay, we got a solution. In fact, this here is now a closed form solution for all potential solutions of this equation. Yay. This actually is very advantageous in the context of string solving in general, because closed form solutions can be used then also for adding additional constraints like regular expressions or length constraints. Well, here another demonstration. This is very simple. It's not applicable here. This the X would look at the right hand side, find a Y, not variable free, and on the other side, the Y would find an X, also not variable free. Sorry, not applicable. And here a third example, it shows, well, we can even introduce powers over powers. So there's still a finite number of candidates we can find. There are only a finite number of candidates where we can fly it to. Okay. Well, there are plenty of rules because now we have to also consider all combinations of a variable against the power term against the character, and so on and so forth. So let's focus on only 4 of them. If you're interested to look at the paper, there we have a nice table of all combinations. But this here is just the rule I showed you before. We can introduce a power by just saying, oh, there's a prefix with variable free. Then we can just introduce here the power. And for example, if we have a power on the right hand side, and we just compare it against the variable, well, we can still split who is bigger, who is the prefix of the other one. Either X just the whole power term W to N is a prefix of X, or well, we just split again. But there is a part of the W to the power of N with the prefix of X. And you can also combine it. For example, if you're comparing here two power terms, well, we can just split on the integer level which of the powers is higher. Similar if we want to unwind it here. However, this requires us to have some combination with an integer reason, which is what I will not discuss. Okay, so far what have we seen? Well, we have string equations, but mostly about aligning tokens. And algorithmically, we just use Nielsen transformation, and we extend it right now with explicit powers, which improved both in performance in cases where Nielsen would terminate in theory, and also it causes more termination, as on some examples where there is no termination via Nielsen, we would actually terminate quite quickly. So now, in the remaining 7 minutes, I will briefly discuss Parikh images, which are pretty cool tricks to make. Find out that certain equations are unsatisfiable, where Nielsen wouldn't help you at all, respectively, although our introduction doesn't. For that, also a brief introduction to what is Parikh image reasoning, what is length abstraction. Well, simple example, if we have a string equation, u is equal to v, then we know, of course, that their lengths are equal. Simple. It's also homomorphism, which is amazing because string equations are not commutative, so plus is, so that's good. And in particular, if you have this string equation here, well, we can just take the length abstraction, cancel out, and we get the length of x is equal to length of y. Great, because if you use this in combination with Nielsen, then x is also equal to y because they are both at start, and therefore a has to be equal to b. Nope. So therefore, we can use that. Another rule is the so-called Parikh image, which is a generalization of length abstraction, and where we just count the number of occurrences of a single character. So let's say we have a length abstraction of x a y is equal to y dx. Well, that doesn't help here. If we just take the length abstraction, it just says 0 is equal to 0. Not really interesting. However, if we take the Parikh image, which just counts the number of a's or b's, well, we just count the a's here. Well, then we get there's one a more on the left-hand side than on the right-hand side. Also not helpful. So this is cool because this equation is something where Nielsen would completely diverge instantly. And it is kind of trivial to see that it's answered, right? Okay, but we can go even beyond and say, what about this string equation? Well, this is also answered, I tell you, but although Nielsen wouldn't find it, Parikh image wouldn't find it, no one would actually find it so far. So we introduced a couple of generalizations. I will present 2 of them to you. One is the multi-sequence Parikh image, and the other one is the multi-sequence error-bounded Parikh image, which is a generalization for the really nasty cases where even the multi-sequence Parikh image diverges. Yes, so let's briefly introduce it. Try to make it short. Well, let's take this equation we saw before. Well, we can just count the PCs, right? If we count the PCs on the left-hand side here, well, there's one on the left-hand side for sure. There might be some in X, but we don't know, we don't see them. And there might also be some in Y, but we also don't see them. Who cares about them? We just put them here. There are some PCs in X, there are some in Y, and there's one additional one. We can do this on the right-hand side as well. And there we see there is no PC here at all. So it's just this term. So, something. But there's a natural question which asks, well, why don't we look for the ABs, for example? I mean, it's a natural question. I mean, there's an AB in the equation book. Why not look for them? Well, we can, but it's not very helpful. It's for certain AB here. We will count it, of course. But is there how many ABs are on the left-hand side? Yes. You don't know. Because if Y ends with an A, well, then there is no AB necessarily in the Y. But in combination with the B, we can see here, there's an additional AB. So we cannot really decompose this further, and we have to keep this very ugly expression here. And so therefore, they will not cancel out, and we cannot do anything, right? So that's a problem. And well, putting into a string-solving terms, AB might be crossing in YB because there's a partial occurrence of this AB inside of the Y, but it's not fully in W, in Y, sorry. Whereas BC is definitely not crossing there. There was no crossing in terms here. There cannot be a BC between YB here or CX here. The rule definitely is not crossing, so this would be fine. So, I mean, we could now just say, okay, let's ignore all the cases in which we have crossing occurrences. But this is also not really helpful because look at this equation here. Everything is crossing. I mean, there we have an X next to an X. Any multi-sequence we're considering is definitely crossing. I mean, if you're considering, okay, AB, well, there could be an AB crossing between the X's here. X could end with an A and start with a B, where crossing. So that doesn't help us much. So that's why we consider group Parikh images and error-bounded Parikh images. So to put it into a nice algorithm, what we are doing here is let's assume we have an equation u is equal to b, and we simply have the same multi-set of variables. So like our equation here. Well, what we do is, well, we choose a pattern. A pattern is just a constant string. Not not the empty string part. An interesting pattern. We have some constraints on it because this set of potential candidates is pretty huge. So therefore we say, well, it's an unboarded string. That means it doesn't start with it doesn't end with a prefix of itself, like this here. This would not be permitted. Always syntactic subsequence of something that's already on the right hand side. And we require it to be maximal. So that means ABC is a candidate, but AB would not be because it's not maximal, therefore longer one. Then we group the left and the right hand side such that there are no crossing occurrences anymore. So here, this ABC goes nicely together. There is nothing crossing, but we cannot decouple these x's because there might be crossing occurrences between them. Well, then we cancel out the common substitutes that occur on both sides. So here the YY crossing both sides, we pick it off, same with the XX, and we just end up with those. Then we replace those variable-free groups that are this pattern by one. In this case, here we have ABC, which is our pattern we are looking for. Here is none, so we have 1 is equal to 0, the conflict. Okay, that's good. And now a final example, which now visualizes the error-bounded Parikh image, which is the heaviest sledgehammer we have for putting these things. Let's take this quite lengthy equation here and say we have the pattern AB. We can write down the whole group here, the whole group in here. Well, we cancel out common things, then we end up with this here. And as you see, there's not a conflict yet. So maybe it's answered. I mean, I don't claim this is a complete decision procedure for anything. So just because it doesn't give a conflict, maybe we just continue by Nielsen transformation. Well, no, actually we don't have to. This is a conflict. Because we can just over-approximate the left-hand side and say, well, we can just assume this here is actually an A. Well, then we just get here A and just say this is still the X and the Y. And we under-approximate the right-hand side. Which means, well, there's nothing crossing between this Y and this X. So we just keep it this way. Well, and as you can see, the left-hand side, which we over-approximated, is now 1 plus XY. And the one we under-approximated is 2 plus the YX. So they can't be equal. Well, we implemented all of this in a sort of prototype called ZIP. And we just benchmarked it a bit against the usual SMT benchmarks for for string equations only. There are plenty of them. And we see in track 1 and 4, well, we are always best. In track 3, there are 5 benchmarks we can't solve. This is mainly because of timeout. This here is the total set of all benchmarks. And yeah, it looks quite good, right? I have to say, however, that this doesn't include regular expressions. These are just string equations only. All right, so what I told you right now is, well, string equations about aligning tokens. You will use the transformation to do so. We have an algorithm that is based on explicit powers and Parikh image and plenty of other stuff that I did not discuss here, like optimized Nielsen rules and integer reasoning in combination with splitting and so on and so forth for a whole set of potential proofs that can hit the equation with. Okay, well then, thanks for your attention, and the capybara asks for questions.